Namaste, welcome to this channel, Dr.ARM's Chemistry. Friends, we were discussing crystal field theory for coordination compounds, and in that case we have seen the crystal field theory for octahedral complexes. Now we will see the next geometrical arrangement, that is this tetrahedral geometry. This tetrahedral geometry is visualized in a cubic structure in this way. So we can draw this cubic shape in this way. This is our cubic structure, in which these are the four vertical faces and two upper and lower faces, and the metal iron is situated at the center like this, and the ligands are occupying the four corners like this. See, these are ligand positions. So these are the ligands. So these represents ligands, and this central metal ion represents in the red circular form, and we can show the structure in this. So these metal ions are having bonds like this, So here the axis is assumed as, this is z axis, this is y axis, and this is x axis, or in other ways we can show like this. So in this way we can imagine the structure. We can imagine this picture in which these positions occupied by ligands are not either in any direction of a ligand or not exactly in between the direction of ligands. These orbitals means we can imagine the orbitals like dz2 and dx2 minus y. So these are lying in the direction of x-axis, y-axis, and z-axis. Whereas the orbitals such as dxy, dyj, and dzx are lying closer to these ligands. So these orbitals are away from ligands. Whereas these orbitals are lying closer to the ligands. So this will show that these ligands, these orbitals which are pointing in the direction of x, y and z axis. So they are being far away from the ligands. The repulsive forces between these ligands and orbitals are very low, or very lowest we can say. Whereas these orbitals are lying not exactly in the direction of metal ligand bond, but they are lying closer to this direction. So this is metal ligand bond. So these orbitals are not pointing exactly in the direction of these dxy dy orbitals, but they are lying relatively closer to these orbitals. These orbitals are lying closer to the ligands, or ligands are lying or pointing the metal ion closer in the direction to the orbitals. Therefore, the splitting of these orbitals is in different way. So we can show this splitting that T2G orbitals are lying at higher level, and EG orbitals are lying relatively much lower energy level, and this is the Davy center. So compared to octahedral splitting, this is exactly inverse. In octahedral splitting, the EG orbitals are lying at higher energy and T2 orbitals are lying at lower energy. But in this tetrahedral geometrical structure, the EG orbitals are lowering in energy, whereas T2 orbitals are rising in energy. So this energy difference between these orbitals is shown in this way. So this is plus 0.4 delta, and this is minus 0.6 delta. So this is also reversed compared to that in case of octahedral structures. The crystal field splitting energy, that is this delta, is represented as delta T. This is represented as delta T. Now if we compare this delta T with that in octahedral complex, that is delta O, then this is given as delta T is equal to 4 upon 9 of delta O. 4 upon 9 of delta O. Means compared to delta O, this delta T is approximately 1/2. It is not exactly 1/2, but approximately 1/2. This is because the excitation of these T2G orbitals at higher energy due to splitting, but the excitation is here relatively lower. So in case of octahedral structure, this difference is 0.6 delta, but here it is 0.4 delta. This lowering of energy of each orbital in octahedral geometry is minus 0.4 delta O. But compared to this, in this case, the energy is lowered up to relatively greater extent. And therefore, most of these complexes are found to be high spin because of relatively smaller energy difference. Compared to octahedral complex, the delta is nearly half, approximately half. Because of this, the energy required for putting electron in T2G is lower than that is required for pairing in the lower energy EG orbitals. So the electrons can easily move into T2G orbitals because the energy required for pairing is more compared to energy required for moving that electron in T2G is much less, and that is why the electrons are moving easily into this T2G. So the complexes, tetrahedral complexes, are mostly high spin, So now we will see the colors of these complexes. So as we know that most of the complexes are high spin. The color of the complexes observed is varying to a large extent, or we can say the octahedral and tetrahedral complexes have different colors. Means if the complexes are having same configuration, then octahedral complexes have different color, tetrahedral complexes will have different color. Now we will see the examples of such geometrical arrangement. Examples. Now if we see the example of a cobalt complex. So cobalt complex gives a low energy distorted tetrahedral system. So such type of complexes are commonly observed when the ligands are strong field. So because of strong field nature, the system undergoes change in symmetry. So the symmetry is changed in order to lower the energy of a complex. And we can see in this example. For example, if we see the complex of cobalt in this way, this is PPH2, this is PH2, this is PPH2. This is a complex that can be represented in this way. PH B CH2 PPH2 thrice COI. Now, in order to attain stability, so this cobalt is at the center. These are the ligands. So this ligand is tridentate. This ligand having boron at the center is tridentate. So there is these three ligands are symmetrical, means of same nature, but this is different. So because of this, the energy of the complex is increasing, and in order to lower that energy of the complex, the geometry consisting undergoes change, and it gives the stable complex. Now we can understand this also by generalization like this. So this is generalized structure. We can have these T2G and EG orbitals. So these are EG orbitals and these are T2G orbitals. In this cobalt complex, the geometry is tetrahedral. So the orbitals are filled in this way. So out of these 7 electrons, first 5 electrons are moving in same speed, moving with same speed, and the last 2 electrons are moving with spin pairing. Now, when the system undergoes change, then this structure distribution remains same. That is EG geometry. But after undergoing this change, 2 orbitals are moving, are becoming low energy. So one orbital gets lowered with A1 symmetry, and 2 orbitals are having E symmetry, and out of 3, 2 electrons are moving in low energy orbitals with A1 symmetry, and 1 electron moves any of these 2 orbitals with E symmetry. So here this distribution shows the change in geometry, and the resulting structure has C3V change in symmetry, C3V geometry. So this structure has C3V geometry, means tetrahedral system undergoes change from tetrahedral to C3V. So this is the relatively higher energy change, higher energy structure, and in order to attain more stability, greater stability, the system undergoes change in this way by changing the distribution. Here in this case you will find all the 3 electrons with same speed, but here 2 electrons with same speed, one with opposite sign. So in this way the system attains greater stable structure. Now we can consider other examples also, such as copper complexes, copper CuCl4 complexes, 2 minus CuCl4 complexes, that is CuCl4 with 2 electrons. And in this case, when here copper is having D9 configuration, means there are 9 electrons in the copper orbitals, and this will undergo a change that is called a distortion, and a high spin D4 complex can also exhibit in this type of change in the structure, that is distortion. A structural change called a distortion is also observed in another type of complexes called FeO4 minus. FeO4 we can have in such structure this Fe distance, the Fe distance, FeO distance is 181 pm, and the examples are Na4, FeO4 or Ba2, FeO4. So these are the examples of D4 configuration. So high spin D4 configurations are shown in this case. So we can consider and we can show the structure. So these are FeO4. Now here we can have the distance between these two as 125 degrees, whereas this distance is 127 degrees. So normally these bond distances means bond angle OFEO or this any, they are expected to be 109 degrees 35 minutes in normal octahedral structures. But these bond angles are changed. It means the normalcy of tetrahedral geometry is disturbed. So this is called distorted. Means the bond angles are increasing. So plane of this OFEO is perpendicular to the plane of this OFEO. Means there are two planes. Say these OFEO are in this plane of board. Then the Fe is in the same place, but this oxygen we can see is lying behind this plane, behind this board or plane, and this O is pointing towards us like this. Means the plane is explained in this. So this oxygen Fe is in this plane, but this oxygen Fe and this O is lying in this plane. So they are lying perpendicular, but their angles with this distances, means this oxygen are moving away. The bond distance is increased from 109 degrees 35 minutes to this 125, and in this case it is 127 degrees. So this is the distortion, and in this case the geometry changes to D to D, right? So tetrahedral geometry is changing. Tetrahedral geometry is changing to D to D, where the bond angles are increased. So this is about the tetrahedral geometry, which is considered in terms of crystal field theory. So with this we will stop our discussion and we will go to the next point, that is square planar crystal field, in the next lecture. So till then, goodbye. See you next time. If not subscribed to this channel, please do subscribe and press like button and bell icon. So thank you very much for watching it. Keep the channel watching.